Welcome back to ChemDoctor, and this video goes out to those hardworking chemistry students up there at NAU and Flagstaff at least down here in the basin on a cold, wet day. So it must be snowing up there. And what we're going to do this morning is we're going to address thermochemical reactions, and these are chemical reactions that either produce or absorb thermal energy. The model system that we're going to look at will be the reaction of propane or the oxidation of propane, where we take propane and we burn it in the presence of oxygen, producing carbon dioxide and water. This is a classic combustion reaction, and the reason I picked it is because I think everybody out there has experience with barbecue grills, and the main gas in a barbecue grill is propane. All right, and so the concepts that we're going to cover here would be similar, though, for burning any kind of fuel source, from wood to gasoline. And with the thermochemical equation, we're basically dealing with a standard balanced equation where the amount of energy that is either released or absorbed is presented. All right, now, so for this reaction, the change in energy at constant pressure, which we call the enthalpy of the reaction, all right, so this term is the enthalpy. It's the change in energy for a balanced chemical equation. That's what a thermochemical equation is. So if we carried out this reaction right now where we combined exactly 1 mole of propane with 5 moles of oxygen, and the reaction went to completion, we would produce 3 moles of carbon dioxide, 4 moles of water vapor, and 2,221 kilojoules of energy. The negative sign means that this energy is being released, and it's thermal energy, which we call enthalpy, all right? And enthalpy is thermal energy, or the energy change that occurs with some kind of a process or chemical reaction at constant external pressure. All right, now, the first thing that I want to address here that you need to understand is that when we write a thermochemical equation like this, the energy value that's shown for it is based exactly on the balanced equation. And this particular reaction is because the energy value has a negative sign, that means that this is exothermic. This is an exothermic reaction. And that means that the energy is released over the course of the reaction. So when you're standing next to this reaction, imagine yourself standing at a barbecue grill. You can see the flame, all right, that's the propane that's burning, and you can feel the thermal energy. Put out your hands, all right, it's like standing next to a campfire. You can feel the thermal energy coming off from it. The human perception is, oh, that's hot, like that, all right? If we draw an energy diagram for this, right, what it's going to look like would be the following for an exothermic reaction. All right, the diagram will look like this. We'll have a platform where we start with the products. There's going to be a hump, which represents the initiation energy to start the reaction. That would be the clicker on the barbecue grill, or it could be a match. You provide the system with a little bit of energy to get it going, and then this particular reaction essentially runs on its own after that because of the energy that it's producing. I'll use R and P to indicate we're going from reactants to products. Notice that the energy where we're starting here, we can write that as H1 for the energy of the reactants. And then when you see where we end up here, this would be H2, the energy of the products. And then if I extend this line out like that, this energy difference here, which is going to be delta H, which is equal to the change in energy, so H2 minus H1, and that energy difference and I'm going to use the negative sign to emphasize, is 2,221 kilojoules. Energy is released. So what does this mean in English? It means that the energy, the potential energy of the products, the CO2 and the H2O that are produced, is at a lower potential energy than the reactants. All right, so they're lower down here on this energy hill. This energy is released as thermal energy, and it can be used to do things. On the simplest level, to warm up your hands on a cold day, or to heat your dorm room right now, as it were, if it's snowing outside. The energy release can also be used, obviously, to cook steaks. Now, let's take a look on a more specific look at how the energy released is related to the balanced equation. All right, so I'm going to rewrite the balanced equation here. Now, since energy is released, and since that energy that is being released is proportional directly to the balanced chemical equation, I want to talk about what that means exactly. So, since the energy is released and is proportional to this balanced equation, in other words, when 1 mole of C3H8 burns completely with 5 moles of O2, then we produce 2,221 kilojoules of energy. So we can treat this energy literally as a product of the reaction. So I'm going to write it in here like this. We can treat this as a product. And the coefficient for this is the same as the coefficient on the propane. It's essentially, like you're saying that for every per mole value, we're going to get 2,221 kilojoules of energy release. So what does that mean exactly? All right, so for the propane, C3H8, all right, if we burn 1 mole of C3H8, we get 2,221 kilojoules of energy released. All right. If we burn 5 moles of O2, because see, that's what's required by the balanced equation, then we get 2,221 kilojoules of energy. If I want to know how much energy is going to be released by this reaction if we burn 1 mole of O2, then it's not this value. So if I want to know the per mole value of energy released by this reaction for O2, we need to divide this number by 5. So in other words, for 1 mole of O2 burned in this reaction, the energy value is going to be 2,221 kilojoules per 5 mole of O2. That's what this tells us from the balanced equation. This is the information that is given to us when we write a correctly balanced thermochemical equation. So this is the energy that is released when this equation operates exactly as it's balanced. So the per mole value for the oxygen is actually going to be, and I'm going to put the sign back here to emphasize that for oxygen, this is going to be minus 444.2 kilojoules now, but to be specific, per mole of O2 burned. So now we have the per mole value. So we could figure out the energy release now for this chemical reaction when we burn any amount we're interested in of oxygen, for example. Similarly, if we wanted to know how much energy is released when we burn a different value of CO2 from 3 moles, then here's what you need to realize about that. All right, so for every 3 moles, of CO2 produced in the reaction, all right, we're going to get 2,221 kilojoules of energy released. If we want to know the per mole value, though, then what we're going to need to do is take the 2,221 kilojoules of energy released for the 3 moles, and we're going to need to divide it by the stoichiometry of the reaction. Right? And in the case of the CO2, we're going to get, I'm going to put my sign back to indicate that this energy is going to be released, because we're thinking about this from the point of view of this reaction going in the forward direction. All right, in the forward direction. So this is going to be kilojoules per mole now of CO2. And so now we could use this value to understand how much energy would be released for any value, for any mass value actually of CO2 that was produced in the reaction. All right. Now with this bit of an introduction, I'm going to go ahead and close this video, and then what we'll do from here is we'll move on to actually doing chemical. We'll move on to doing calculations using this concept.